last class we covered the first come first serve, show this job first, as well as show this the remaining job first. So by the way, what is a scheduler? What is a CPU scheduling? It coordinates the resource. One of the main purposes of the operating system is we'd like to coordinate, control the computer resource because we have very limited computer resource, but we need to support the multiple processes. Okay, that is the main reason. So we need a lot of the such a scheduler in our operating system. This is the most important scheduling. In other words, it's called the short-term scheduler because it is quickly changing within millisecond level. Okay, so how can we schedule? Because the CPU time itself is not reduced, it's not increased. Instead, we try to maximize the CPU time. Okay. However, 100% the CPU utilization does not mean it's the best. The scheduler, the 100% CPU utilization usually means it's something wrong, like the infinite loop. Even operating system scheduler itself is what? It's a processor. Even that process cannot get the CPU resource. So we need to, however, our goal is to maximize the CPU utilization. To do that, so we discussed several things, and today we are going to cover the CPU scheduler. However, as I mentioned many times, all of these scheduling algorithms are based on what? Certain different priority. Okay? When we talk about the first come first serve, what is the priority? Arrival time is the priority to select the next process. From where? Ready queue. So we have the process state. New process will move to the ready if it is ready to be executed. Okay, then dispatcher, CPU scheduler will select one of the processor by using one of the algorithm. Okay, then it will move to the running state. Then, in case of I/O or the wait, it will move to the I/O wait. Then the dispatcher will select another process. Then once the processor receives the return of the data request from the controller, it will move to the ready queue again. Okay, then the dispatcher, whenever there is a new process in the dispatcher at the ready queue, dispatcher will be activated to select the next process. Then once the process in the running queue is terminated, also the dispatcher will select another process using one of these algorithms. So these are based on the priority. Show this job first. For example, the size, the total amount of the CPU burst time is the priority. The smaller is the higher priority. Why don't we consider remaining job? Okay, that is assuming the remaining time first. And today we will see the last class we have seen the priority itself. We assign explicitly the priority number. Okay. Normally, most of the operating system uses 0 to 15. Okay, 1 to 15, the priority. However, the Windows use the 5 different levels as we have seen before. Okay, the real-time processing or the low, the priority, something like that. Okay, so we can assign such a priority. So this is the Gantt chart to understand the scheduling algorithm. This is the example of the first come first serve. So as I suggested, when you solve probably I'm not going to ask such a simple question in your midterm exam. It will be more complicated. Okay, do not believe the memory. So instead believe your hand. So please practice by yourself. It doesn't take a long time, just a couple of minutes. Why don't you practice by yourself? So with the hand or your scratch paper. And the average waiting time, average response time is not very complicated as long as you understand what is the waiting time, what is the response time. Okay? So using definition of the waiting time and response time, you can compute the average waiting time, average response time. Why do we need this one? To judge, to evaluate the scheduling algorithm. Okay. So what is the waiting time? It's a total amount of time the process, each process wait until terminated. Okay? You need to sum up all the waiting time. However, on the other hand, the response time is a slightly different slide. The response time is the total amount of time from execution and first response. That is so different. Then, so I strongly suggest you to manage the ready queue on your right hand side, whatever. Then manage your ready queue. Okay. Then you probably successfully finish to understand such a scheduling algorithm. Shortest job first, we can consider the length of the total CPU burst time for the priority. So we will select shortest one first from the where ready queue. Okay. So this is the example of the shortest job first. Non-preemptive means once the process is started, it will be completed. Okay. No other guarantee to be resumed. Okay. No backup. Okay. Preemptive case means it can be stopped depending on the situation. Like if there is new process arrival time, then at this time you will check. Okay. Then pick up the process who has the shortest CPU burst time. Shortest remaining job first will consider, for example, at this time 12, remaining time of the process 1 will be 5. So instead of 7, you can consider 5, 4. Which one is shorter? At the time 4 is shorter than the P1. So P1, P2 will be selected in case of preemptive case of shortest job at the shortest remaining job first. Okay. And then one of the main problem of the such a shortest job first, shortest remaining job first is to determine CPU burst time. Actually, practically it is not possible to know the exact CPU burst time, even though you already know. So even though you learn to execute the same program with the same exactly same situation, sometimes it takes a longer time, it takes a shorter time. That happens. Okay? So how can we determine? We can guess. Okay? Based on the previous state. Okay? Based on the experience. So in other words, we can define how the current state, current time, what is. So we are not going to use the continuous time. Instead, we have the certain amount of time. In other words, it's a discrete time slot. So N0, 1, 2, 3, 4 means it's a time, discrete time. Okay, at this time, how many CPU times are required? Okay, based on what? The previous one. Previous the CPU burst time, and this is the expected the expected the CPU burst time at the time. So we can adjust with the alpha is the parameter value. So like this one. So we can have the term n+1. n+1 means next time slot is based on the previous one. Okay, we can reasonably guess such a guess is used a lot. Okay, so for example the fire nation, okay, or even the traffic system, whether car will be accident or not, something like that. So there are a lot of applications to predict the next stage. One of the examples of such the prediction model is Kalman filtering. So if you are doing the research in the PhD level, probably you heard about the Kalman filtering or extended Kalman filtering. That is the education model. It's a statistical model. Anyway, the next one is the priority scheduling. As just like the other, any priority-based algorithm, it has the problem of the starvation. Okay, those who has the lower priority may not get a chance. Okay, so how can we address the problem? We try to promote their priority by the time, along the time. That is called the aging. Eventually, the process can get the highest priority which means it can get the CPU resource. Okay, so this is the example of the priority-based CPU scheduling algorithm. We have the this kind of the CPU state, processor state. Process 1 allows the time 0 with the CPU burst time 19, but it has a priority. Where can you find? If you are asked, okay, to implement this CPU scheduling algorithm, where can you manage such an information? Ready queue? Ready queue has all the information. Ready queue has the process information. But ready queue manage what? All processes. You don't have to keep the all processes. Instead, process, control, block, the PCB. Okay? So in other words, if you need to implement such a CPU scheduling algorithm, you need to manage, you need to define PCB structure. Okay? That is the same as the operating system. So operating system, when operating system has been developed, the developer of the operating system, they define what is a PCB structure. So even though that is simple in your program, anyway, you need to create such a processor control block structure to manage such a information. Okay. That's what you need to do in your project 1. Okay. So it has a priority. Which one is the higher priority? P3 or 1?
P3.
1 or 3. So process 1 or process 3? Process 3. Lower is the higher priority. Okay? So don't be confused. So non-preemptive means what? Once it's started, it will be terminated. Preemptive means it can be resumed. Okay? It can be back up. So we can reconsider whenever there is the event. So non-preemptive case at time 0, as I suggested, I strongly suggest you to manage the ready queue. So I have my own ready queue. This one. In the ready queue at time 0, the P1 is alive with the arrival time, CPU burst time, priority is 3. So dispatcher, your CPU scheduler will select one of them based on the priority. This is the only one, so select it. Because it's a non-preemptive, it will be terminated how long? 19. 19 times slot, it will be. Meanwhile, the process 2 is alive time 2 with the CPU burst time 10 and priority 2. And P3 is also alive time 4 with the CPU burst time 7 and priority 1. So at time 19, so we do not have the P1 because it's terminated, right? So among P2 and P3 from the ready queue, which one will be selected? P3 because it's the higher priority than other processes. Even though you have the processes, you don't have to worry about. Okay, then P3 is selected, will be terminated in the 7 time slot, so it's a 26. This is the only one. Then P2. What about the non-preemptive case? Preemptive case, we have the P1 is selected first time and alive time 0, CPU burst time 19, and CPU time 3 at time 2. Because time 2 P2 is selected, enter the ready queue, alive time 2, and the 2. Okay? Your dispatcher scheduler is activated. You need to select one of them based on one priority. This is the lowest priority. Highest priority, lowest number. So P2 is selected. So P2 is selected. Actually, this one moved to the running queue, but I'm not going to manage the running queue. Okay, instead mark such a thing. And time 4. Time 4, P3 is alive 7, 1. So at time 4, we need to select one of these. Okay, which one will be selected? Highest priority. P3 will be selected. Probably it will because it's a highest priority, there's no other event, so it will be terminated. So it needs a time 7, so it will be 11. In the 11, so we have 2 processes, P2 will be selected. Remaining time is 8 because it already used the 2 time slot. So will be terminated, then Q1 like that. Then you can compute the average waiting time, average response time for each. For example, the average waiting time of the non-preemptive case is 13, and average waiting time of the preemptive case is 8, which means the preemptive case of the priority based CPU scheduler is better in terms of what? Waiting time. Okay? In terms of waiting time, the preemptive is better than the non-preemptive cases. Okay. The next one is the round robin. Round robin means, what is a round robin? It's a round robin. It takes a turn, takes a turn, takes a turn. When you have the competition, it's not like the tournament. So sometimes, so do you like the World Cup soccer game or cricket game or something like that? So in the tournament, before tournament, there is a group A, B, C, D. Each group has a round robin. Okay, they play the game each other. So each team will take the round. So we are going to make the round of the CPU time. Okay, round 1, the first turn, second turn, third turn. So fix the time slot. Fixed time slot, then allocate the next process. If that is done, and turn around the next turn. Okay, that is the round robin, the CPU scheduler. We will see the example. So we have currently all the process are alive at the same time. P1, P2, P3, P4, and CPU burst time is 53, 17, 68, 24. First, we need to decide the time slot, the size of the time slot. Okay, let's say that is 20. So we are going to segment the CPU time by 20. Okay, but in this case, the 20. So first one, we are going to assign based on the, let's say this is the order of the process. We will use such an order as it is in the ready queue. The P1 will take the 20 time slot. Okay, so remainder is 33. Then next, P2. However, P2 is the less than 20. It's less than the time slot, size of the time slot. At that time, there might be 2 options. Okay, one option is we are going to allow only as needed, which means the 17. Okay, or you can assign no matter what size. It's just a fixed size. The later second case, there might be the waste of the CPU time. So it is not used. However, that one is very simple. You can segment the CPU time by 20, 20, 20, 20. Just assign. However, it may have such a waste of the CPU time. So which is not used a lot. So we are going to use such a 17, the first option. So allocate the 17 as needed. So this one is terminated. The next one is the P3. P3 will take the 20, so 48 remainder. Next one is a 24, remainder is a 4. Then go back to the first process, 20, then it will be 13 remainder. This one is already done. 28, P3, and 4 is done. That is the reason it needs only 4 time slot. Okay, and so on. Okay, this approach is the round robin approach. At that time, this time slot is called quantum size. Okay, this is a quantum benefit. in general, this is the most fair approach because it's round robin, right? So this is the most fair in general. However, if you consider certain priorities, not fair. Because I'm very busy, if I'm not running, for example, I'm this schedule, okay? If I'm not running, no process can select it, okay? So it depends on, however, in general, it's fair, the algorithm. Also, it provides fastest response time. No matter what priority, no matter when the arrive, it will get them quickly. The CPU resource, even that is not enough to be terminated, which means it has the very good response time. So it has the very good response time. Okay? So it provides a very good response time. It's a better response time. Problem. What is the only parameter used in round robin? Variable. It's the quantum size. Okay? What is the quantum size? Optimal quantum size. 20, 30, 40, 100? We don't know. Okay? Depending on the quantum size, it can be different algorithm. For example, let's say quantum size is the 1 million times 1. Too big. Okay? No other process is bigger than the quantum size. That is the same as what? First come, first serve. Right? Once it is started, based on the arrival time, it will be terminated. Because quantum size is big, so it will be a first come, first serve. So deciding the quantum size is the problem. Okay? So how can we address the problem? Any opinion? Let's say in computer system, in operating system, we can classify the process into two groups. One is online transaction processing, okay? Which means it requires very quick response time. Like the what? Banking transaction or the network transaction. So it should be executed very quickly. Okay, that is one of the jobs. Usually foreground job. On the other hand, there are service program. In other words, background program. It runs forever. Just like the life of the operating system, it should be running. Okay? Like what? Scheduler and some other batch job. So that means it doesn't require very quick response time. It needs the what? Throughput. Better throughput or turnaround time. So at that time, the first case, we need round robin, for example, because it provides quick response time. The second, background processes or batch process, it needs first come, first serve. Once I receive the CPU resource, it will be terminated. So can we adjust such a thing? No. Round robin, we cannot. We cannot change the quantum size dynamically. So to address that problem, we can design such a multi-level queue scheduling. So how many queue we have in general process state? Ready queue. Okay, I know we have the different queue for each device. Okay, but in CPU scheduling in general, we have the one ready queue. From the ready queue, CPU scheduler select the process. What if we design different the queue, number of queue? This is a ready queue. Okay, one ready queue, but inside the queue we have many queues inside. Each queue has their own characteristic. First one, for example, system process, like the scheduler or the disk scheduler. And the swap processor. So this is the system processes. They need to get the CPU resource, okay? But not entirely. So sometimes it doesn't require any quick response. Okay? And another one is interactive processes. It needs the feedback between user through the interface. Okay? That need very quick response time. When I type a keyboard, if it takes a long time, you will throw away your laptop, right? Should be response quickly. So that is an interactive process. What about the batch processes? Batch process usually takes a long time. Doesn't require quick response time. However, it needs the less turnaround time. Should be completed. It takes usually 1 day, but what if it takes several days? We don't like that. So it doesn't need any quick response time, but it needs the higher throughput or the shorter turnaround time. I don't know why this guy put the student process. The bottom, it looks like the student process. It's not important, right? But anyway, we can classify such a type of process. Then design the multiple queue. Then what? Assign different scheduling algorithm. Okay, this one is a round robin, time quantum, the quantum size 8. Round robin, quantum size 4. This one round robin, quantum size 16. This one is first come, first serve. Okay, this one is a first come, first serve. Or something others. Shortest remaining time first. Here, something like that. We can assign different scheduling algorithm. Then we can address the problem of the round robin. Round robin, we cannot dynamically change the quantum size, but using this one, we can do that. Problem. A benefit? Yes, we can dynamically. It looks like the dynamically change the quantum size. So depending on the characteristic of the process, we can assign different scheduling algorithms. So it will be good. Problem. How many CPU do you have in this algorithm? For this algorithm? Only one. Still one processor, which means you have the time slot. Then anyway, you are going to select only one process among multiple queues, which means first you need to select one of the queues. In other words, you need to schedule queue. There are two steps. One, scheduling queue first. Then schedule for each. It's overhead. Okay, and more complicated. Another problem, inside the queue, for example, first come, first serve, it has the general problem of the first come, first serve. So, for example, once it get the round robin, not that one, not that way. Another problem is we need to classify the process, one of this. How do you know this is the batch process? How do you know whether this is a student process, system process? Sometimes, if that process is a general process, you can know. You already have the information. What if I submit the ABC job? Whether this is an interactive process, whether this is a batch process, whether it's a student process, sometimes it's not possible to identify which queue the process belongs to, right? Unless the system administrator or developer or user explicitly specify the queue, okay? So that is another problem. Multilevel queue is good for dynamically changing such a scheduling algorithm depending on the characteristic of the process. However, how can we determine HQ, the process bloom, right? So how can we address that? At that time, we can define feedback queue, multi-level feedback queue. Let's take a look at this. We have multi-level queue, like the previous one. Okay. How many queue we have? 3 queues. Okay. First one is quantum round robin quantum with the quantum size 8. Okay, which means you can get 8 time slot. So next one is round robin with quantum size 16, a little bit longer. And last one is first come, first serve. We are not going to determine which queue is assigned the process. Instead, process always enter this one. Quantum size smallest quantum size. Okay? Then, if the process is not terminated using one quantum, it will move to next. Otherwise, which means if terminated, it's done. It's terminated. If the process is terminated, which means the CPU burst time is equal or less than 8, terminated. Otherwise, move to the next queue. Then, if that is done with the time slot 16 and terminated, otherwise still remain the how big is that? Bigger than 24. CPU burst time, it will move to first come first serve. What is the first come first serve? It will once it is started, it will be terminated. So usually interactive process which require quick response time, okay, or short amount of the CPU burst time will be completed the beginning. However, if the process takes a long time, it will move to the next. Finally, in the first come first serve, it will be terminated. So this is called multi-level feedback queue.
So
Okay?
it accesses the highest priority queue first.
Highest priority, we do not specify the priority.
So whichever is on the top, that is the queue.
Yes, that is the first one. Okay? Because it starts enter, it's always here. Okay? We don't know. However, somebody may be curious. How many CPU we have? Only one CPU. How many queues? 3 queues. How can they share? You need to assign. For example, this is 30%, 30%, 40%. Or you can schedule along the queue you need, because it's anyway multi-level queue. You have the multi-queues. Okay? However, you can give the highest priority for this. There are many different ways to implement multi-level feedback queue. Because of that, one of the problem of multi-level feedback queue is too much complex. Okay? Not as simple as the previous algorithm. Because you need to design along the queue level, and for each level you need to implement a scheduling algorithm. Yes?
So let's say if we didn't have first come first serve as a third one, and third one we had quantum equals 4. And how even after that it didn't finish.
So that is the reason it is required in multi-level queue. The first one, the top one usually has the shortest the time quantum, then increase. Because it looks like the very fine filter. Okay? So you can actually get in the bottom of that, you will have the fine grain, the sand, for example. Okay? Then next, we have a little bit. Why? size of the same. The last one, the other kind of route. Same approach. Okay? It's kind of filter for each the level. Okay? Then we don't have to worry about what is the characteristic, how long it takes. Okay? So automatically the finish it, if that is short and that requires the first response time, it will be done. Otherwise, it will move to, if that is the process takes a long time, that will move to the first come first serve. So this is called multi-level feedback queue. Okay? However, this one requires a lot of parameters. Okay? You need to decide each the queue. And also you need to decide the scheduling of the along the queues. Okay? So let's take a look at the example of such a multi-level feedback queue. Very nice. I have 3 layers, the lower body, 4 layers upper body. So very hot in this one. But you do better. This is my first year to have the multiple layers. I usually wear just a single layer of the pants, but once I got the flu, I changed my mind. But inside the room, very hot. Okay, so actually this was the project last semester. The student implemented multi-level feedback queue. 90% of the students actually couldn't understand what is the multi-level feedback queue, so I made this slide for students to understand. After the student see this slide, most of them understood, then finished the implementation successfully. However, this semester is a different. Okay, so we have the the queue, multi-level, 3 levels of queue. First one is, as I introduced before, it's a round robin with a quantum size 8. Next one is a quantum size 16. And first come first serve, actually we can understood quantum size, the first come first serve as the round robin with quantum size what? Infinite. Big enough, right? This is actually round robin. So some students actually implement separately for each level. However, you can just implement one algorithm, round robin only. So I didn't mention, so those who use such a technique get the better credit at the time. Okay? Anyway, so we have the 3. So once requirement is process enter this one first, quantum size 8. If that is done, yes. Otherwise, move to next. If that is done, terminate. Otherwise, move to first serve. But finally, it will be complete. Also, I give the scheduling, the requirement of along the queue, which is quantum 8 is the highest priority. And next priority and lowest priority, which means if there exists any process on the first queue, no the other queue can take the CPU. It's a priority-based approach. So highest priority, medium, and lowest priority at the time. So by considering this one, so you can see the priority-based queue scheduling, Q0, Q1, then Q2. Okay? Then this is the common mistake. The students are struggling, how can I manage such an information? Only PCB using process control block. What is a process control block? What is that? It is data structure. It can be struct in terms of C program. It can be object in terms of object-oriented program. Okay? You can define. In terms of database, it can be the table. Right? So it's not that special, it's a data structure. Okay? But I'm surprised, even those who already got the computer science degree, master degree, even PhD degree, they do not know such a data structure concept. So everything that we discuss, it can be understood as a data structure. This can be easily implemented data structure. You can define your object file for the PCB. Then, whenever you have the new process, you can initiate that object, classify, that's it. Then, in the scheduler, you can, for example, what about the queue? It can be managed as a queue structure, or you can use the vector even. You can use the list object if you are using Java program. So that's it. It's actually quite simple, everything. Process can be created randomly, more than 20 processes. So this is just the example to demonstrate the multi-level feedback queue. So we have the process state, how many processes, 10 processes, and different arrival time, and CPU burst time is here. At time 0, nothing, okay? It's a nothing. And time 2, P0 is alive. It should enter the first queue, Q0, okay? So what is the priority along the queue? Q0 should take the CPU resource, even though there are processes, Q1, Q2 cannot get, okay? So PQ0 has the one process that requires 10 CPU burst time. What is the CPU burst time of Q0? 8. So it can get Q0, the process 0 can get the 8 CPU time. Okay? So time 8, P1 is alive. So P1 is alive. However, the P1 need to take 8 CPU burst time. Right? So here 8 means it's a time 10. Time 10 P1 is not completed, right? So which means it moved to the next queue. Okay. Also P1 is alive at that time. P1, no P1, P2 is alive with CPU burst time 35. So this is the current state. Then first you need to run scheduling algorithm of what? Along the queue. What is the rule? Priority. So this one takes the CPU resource. Even though we have the process, Q1, Q2 cannot yet. So this one takes the CPU time. Then what is the algorithm of Q0? Round robin of what? Along the process with the time quantum how? 8. So which one will take the CPU resource? P1 or P2? P1 alive first. So P1, P2, P1, P2. However, it takes only one round, right? So P1 is done because it's less than 8 time quantum is done. Okay, that is the benefit of multi-level feedback. Even though we do not know P1 is an interactive process, a batch process, doesn't matter. Okay, if that is short amount of time, it will be done here. Time 17, even though that is not the 8 time cycle, because the one process is terminated, CPU scheduler will be activated. So, which one? Q0 or Q1? Q0, because there exists the process. So Q0 will take the CPU resource inside the Q0 round robin with time quantum 8. So P2 take the CPU time 8 times slot. Like this. But it's not terminated. So it will move to the next. At this time, we need to run what? Scheduler for the along the queue. Priority base. No process, and this one has a process. So Q1 take the CPU resource. Then run the scheduling algorithm for Q1, which means round robin, time quantum 16. So one process will take the 16. So P0 alive first. So this one will the first round will be done because it needs only 2 times one. So we can keep updating the Gantt chart. Then this the time 27, this one is the only process can take the CPU resource. Okay, but time 30, P3 is alive. Okay, P3 is is alive. So new process. What happened?
Q0 will execute.
Q0 will be executed. Okay? Because it has the highest priority. So it will take the, you can see the 18 will be at 35, but still the P3 will take, because this one is the, still one time quantum. And so on. This is the process. Finally, for example, in this case, Q1 exists in here. So Q1 will be selected at process A will be terminated. Then finally, this process will be terminated at the Q2. Okay, this is the multi-level feedback queue. Then you can compute the waiting time based on this. You can compute the turnaround time based on this, and also average response time based on this. Actually, that was the project last semester.
What is turnaround time?
Turnaround time, total amount of time to be finished one process. It includes a waiting time, starting time to end time. Okay?
Even
Yes.
for that, for example, one process even gets started at wait time 0,
Mhm.
and then there is another process which gets started at for example P2 at 10,
Mhm.
and then again that P1 gets started at 15.
Mhm.
So what will be turnaround time for P1?
P1 start. P1 start time 0. Then, so for example, P1 takes the time 5, okay, and wait up to 10 and 15 is completed. Then the turnaround time is the 15, include the waiting time. Okay. So this is a multi-level feedback queue. So if you can understand multi-level feedback queue, you should be able to all the scheduling algorithms.
Now when we write the code for the scheduling, where do we store it? Does it get stored in the terminal?
So we will discuss it after we finish this chapter. Okay. So regarding to the project 1, so once we finish this chapter, I will explain more in details. Okay. So that is a multi-level feedback queue. It's a very flexible, but the problem is very complex to design and implementation. Okay, but this is mostly commonly used the scheduling algorithm in the contemporary operating system. What about the thread? What is a thread? Basic process. So it's a process. Yep. You need to study hard for your midterm exam. Okay. So what is a thread? Thread is a process. It's kind of process, but thread is lightweight process. Okay, which means it's a part of the process. Inside logically, one process has many threads of instruction. Why don't we separate like the function? So lightweight processes, but it's not process. So multiple process can create multiple threads. Okay, that is a thread. So, however, each thread acts as process their own function. How can we schedule? Each thread needs a CPU resource, right? Because it's a series of instructions. It has their own series of instructions. How can we schedule?
Using same algorithm.
We need to consider scheduling of thread. Okay, so the thread can be considered as the processes. Inside the process, we can separately schedule. However, in terms of operating system, they belong to the same process. So there are the thread scheduler for each process. Right? Then they thread the schedule for that thread. Okay?
The idea of thread isn't it same as forking in EXTC command? Because technically thread also creates a copy of the main process. And
No,
it starts
it's a different system call.
executing.
No, it's a different. It's a fork and EXEC. Is it same as the fork and EXEC for the thread? No. The fork and EXEC, when you create the process, the fork and EXEC, when you fork, that copies. Okay? But it's just clone. Okay? But thread is different. Thread, you can share as many the structure as possible with the process, then separate. So take out the instruction part, okay, and their own step and their own the thread information, okay, separate. So the other you share just the existing process. So that is the reason we don't have